Hello everybody and welcome to this GCSE Chemistry video where we will be looking at reversible reactions. We'll be focusing on exam questions, and what I will do is I'll show you the exam question and I suggest you pause the screen, and then what I will do is I will talk out loud for my thoughts and I will write some of the reasoning down in blue as we look at the question, sort of thinking out loud. But then what I will do is I will write down the answers in green that you need to put down to get yourself all the marks. Okay, this first question is about the production of ethanol in industry, and we're told some details about this. We aren't expected to know this for GCSE Chemistry, but we are expected to be able to work with unfamiliar situations, and so we can see that ethene and steam are reacted together, and here they are in the chemical equation over here. And so they are reacted together, and we've been given some conditions: 300 degrees C and 60 atmospheres, and using a catalyst. So similar setup for what you do need to know about the Haber process they've presented for us here. Now we're told it is a reversible reaction by the use of this symbol here, the sort of the equal sign with a little flick at the bottom and the top showing it can go forwards and it can go backwards. And here is the ethanol on the right hand side. So we've got a flow diagram about the process where the ethene and the steam enter on the left hand side, and then they go into the reactor, which is the part that will be at 300 degrees C and 60 atmospheres and have the catalyst inside. So that will be where the sort of the business end of this reaction is taking place. And then we've got an arrow pointing downwards to the separator, and we've got a mixture of ethanol and water coming out of the separator, and then unreacted ethene is going back into the reactor. So quite a lot of parallels with the Haber process here. So the first question says, why does the mixture from the separator contain ethanol and water? Now there's quite a few different options that we can write down. First of all, ethanol is a product and water is a reactant. So why does it have both of them? That's kind of why that makes sense as to even be asked as a question. But the simple answer is it's a reversible reaction. And so what that means is you will have some of the products, the ethanol, which is here, and you will have some of the reactants as well. So here is the water and here is the ethanol. We've got them both because this reaction is reversible. Now, a slightly more complex answer is involving these state symbols. So we've got a gas, and we've got a gas, and we've got another gas. So how is it that they're separated? Well, just like in the Haber process, where the ammonia condenses and the hydrogen and the nitrogen get pumped back round into the reactor, a similar thing happens here. The water vapour and the ethanol will condense, and that means that the ethene is the only thing that is still a vapour. The ethanol and the water vapour have turned into liquids. Of course, you wouldn't need to say both of those things because it is only 1 mark. Now the second question gives us another fact. The forward reaction is exothermic, so that's the reaction that goes to the right. Use Le Chatelier's principle to predict the effect of increasing the temperature on the amount of ethanol produced at equilibrium and give a reason. Well, Le Chatelier's principle says that equilibria shift to oppose change. And so that means that whatever we do, equilibria will shift in the direction that reverses or opposes that change. And so in this situation, we are increasing the temperature. And Le Chatelier's principle tells us that the equilibria will shift, so EQM, I'm going to abbreviate that to mean the equilibrium. The equilibrium will decrease the temperature. And so what the equilibrium will do is it will shift in the direction that brings the temperature down. So exothermic reactions increase the temperature, and so endothermic reactions will be lowering the temperature, and that will be the shifting to the left. So the language that we need to say is that the equilibrium will shift or move to the left-hand side. And this will have the effect, when the equilibrium shifts from the right-hand side to the left, so it's shifting left, that will have the effect of making less product. And so the amount, because let's not lose sight of what they've asked us to do, comment on the amount of ethanol produced, the amount will decrease. And so what we might sometimes get is we might sometimes get a 3-mark question, and we've only got a 2-mark question here, which we've already secured both of the marks. But if it was a 3-mark question, we would want to be saying what we've got written here about the equilibrium has shifted to decrease the temperature, but not necessary here to secure the 2nd mark. In a similar sort of way, this follow-up question is also only 2 marks, and sometimes it can be 3. But here we've been asked to comment on how the increase in pressure will affect the amount of ethanol produced at equilibrium. So remember, we need to comment on the amount. So let's return to our equation up at the top. You can see that we've got ethene, 1 mole of ethene, there's no number there, which means 1 mole, reacting with 1 mole of water, and we're making 1 mole of ethanol. And so there are 2 things on the left-hand side, and we've only got 1 on the right-hand side. And so compared to each other, the 1 can be considered to be a lower pressure, and the 2 is the higher pressure. So we've got 2 sides here. The reactants are the higher pressure side, and the products are the lower pressure side. And as we have already said, the equilibrium will shift to oppose the change. So we have increased the pressure, and the equilibrium wants to decrease the pressure. And the reaction that decreases the pressure is the one that shifts to the side with fewer moles of gas, because that will be the lower pressure side. So the equilibrium on this occasion is going to shift to the right-hand side. So that's what we need to say for our 2 marks. The equilibrium will be moving to the right-hand side, and that will cause more ethanol to be produced. Instead of saying equilibrium shifts to the right-hand side, we could say that equilibrium shifts to the side with fewer molecules of gas. That's a suitable alternative, and it would be the important 3rd mark if it had been a 3-mark question, but this is only 2. This next question is actually also about the production of ethanol from ethene and steam, but they ask the questions in a slightly different way, and hopefully that's been good practice having a go at it. So first of all, they ask us what is meant actually by the term equilibrium. And so an equilibrium, it's not enough to just say that it's a reversible reaction. What we need to say is it's a particular kind of reversible reaction, and the forward and the backward reactions are occurring at exactly the same rate. So that's our first 1 or possibly 2 marks, depending on how generous the mark scheme is. For the development of this, we need to say that it only happens in a closed system. Now, a closed system is one where nothing can get in or out. No matter can get in or out. So a beaker with some chemicals in it, that's what's called an open system. And a closed system is simply one with maybe a lid on the top, so nothing can get out of this beaker. No matter can get out or in. Energy can still get in or out though. And so the optional 3rd mark is to say this in a closed system sentence, but instead we could say that as a consequence of the forward and backwards reaction happening at equal rates, the amounts of the reactants and products remain constant or remain the same. You'll recognise these next 2 questions, so I'll do those quickly. So the question is saying, how would increasing the temperature change the yield? This time they're using the word yield, but that's just a fancy word for amount, and they use it in the next question as well. And so we are increasing the temperature, so that's what we are doing, which means, as we know, that equilibrium is going to shift to bring the temperature back down, in other words, the endothermic direction. And so what we have to do is we have to look up at the original information that we were given, and that negative sign for the delta H is crucial information here. So delta H means the energy change, and the fact that it is negative, that means that this is an exothermic reaction. And when they give information like that, they're talking about the forward direction being exothermic, which means that the backwards direction is endothermic. And so what we need to say is that increasing the temperature will lower the yield because the backwards reaction is endothermic, or the forwards reaction is exothermic. That's actually all we need to say here. We could say that the equilibrium is shifting left, and that would lower the yield. Either of those is fine. And for this next question, we have increased the pressure, and so the equilibrium will be decreasing the pressure, and to do that it shifts to the side with fewer molecules of gas, and as we discussed previously, there are fewer molecules on the right hand side, which means the right hand side is considered to be the lower pressure side. So all we would need to write is that increasing the pressure is going to shift the equilibrium to the right, or shift it to the side where there are fewer molecules of gas, and that will increase the yield because we're making more product. The amount of product has gone up. If you don't want to say fewer molecules of gas, you could actually say 2 molecules of gas on the left-hand side, but there's only 1 on the right-hand side, so you could actually give the specific number. Either way is fine. And then this final question asks how catalysts increase the rate of a chemical reaction. So there is one non-negotiable fact that you need to say for our 2 marks, well, the first of our 2 marks, and that is that catalysts lower the activation energy. And the activation energy is the minimum energy needed to start a reaction, which brings us on to our second point then, which is that less energy is needed for the particles to react. The alternative second mark could be gained by exploring how the catalysts have lowered the activation energy, and that is by providing an alternative pathway. So you could say that instead of commenting further on the energy. This next question moves on to a different reversible reaction, but we explore a number of the same themes. So it says here, reversible reactions can reach equilibrium in a closed system, and what is meant by a closed system. So as we've already explored, a closed system is one where nothing can enter and nothing can leave the reaction vessel. Or alternatively, you could just simply say the reaction vessel is totally sealed. And then the next question says, the reaction appears to have stopped in reversible reactions, and we've been asked to explain why it appears to have stopped. And that comes down to the reversible reaction symbol, and you've got your reactants turning into products, and that is happening continuously at exactly the same rate. And that's what you need to say. The forward and the backwards reaction have the same rate, so there is no overall change in the quantities or amounts or concentrations of the reactants and products. And then we move on to the nitty-gritty of the Haber process, which is where we make ammonia from nitrogen and from hydrogen. And the question says, name a natural resource from which hydrogen is produced. And hydrogen, there's actually a clue there, natural. Hydrogen comes from natural gas. We could also say methane, we could say fossil fuels, either of those or any of those is absolutely fine. We could even say from water, actually. You can get hydrogen out of water if you are prepared to do electrolysis first. Now, as an aside, we've not been asked here, but the nitrogen comes from the air in the first place before we use it in the Haber process, and so that could have been an alternative question to this one. Then the question goes on to ask us about catalysts again, and so this is almost an identical question in fact, and so what we need to say as to how the catalyst speeds up the reaction is catalysts provide an alternative reaction pathway, and the second mark is for saying that this has a lower activation energy. And then the final part to this question says, what happens to the amount of ammonia produced at equilibrium if the pressure is increased? And we have had this same type of question before, so we need to look at the equation itself, and we see that there is 1 nitrogen on the left-hand side and 3 hydrogen, so a total of 4 molecules on the left-hand side and only 2 molecules on the right-hand side. And so the right-hand side can be considered to be the lower pressure, and therefore the left-hand side is the higher pressure. And so we've been asked what happens if the pressure is increased. So we are increasing the pressure, and equilibrium wants to decrease the pressure, and the reaction that decreases the pressure is the one that goes to the right, because that is the side with the lower pressure. And so what we need to say is that the amount of ammonia will increase, because here is ammonia on the right hand side, and that is because the equilibrium has moved to the side with fewer molecules or fewer moles of gas, or the equilibrium has shifted to favour the forward reaction. This next question is still about the Haber process, but this time, instead of being a lot of little questions, we've got one continuous space for you to write your answer in, and we've got a graph for you to interpret before attempting the question. And so if we have a look at the graph, we know about the Haber process, we've been told about the conditions that are used, but we need to explain why. And so what I recommend you do before you actually start in the question is just try and make sure you make sense of the data, because it might be for a completely unfamiliar reaction. And so what we can see is we've got pressure on the x-axis and the percentage of ammonia on the y-axis. Now the percentage ammonia is an alternative way of saying the amount of ammonia, or more precisely, the yield. And so what we can see is that in general, the graph goes up like so. And so we can see we've got a positive correlation tending towards 0. And so what we can also see is that as we go to the right then is an increase in the pressure, that is increasing the yield. So that will definitely come in useful as we answer our question. And then the second thing to note is that we have actually got 5 different temperatures, and we have got the lower temperatures at the top and the higher temperatures at the bottom. And what are they showing us? Well, if the lower temperature is at the top, that is telling us that decreasing the temperature is increasing the yield, because the higher temperature, 550, is the lowest down. If we scroll to the left, we see we're about 20% yield, whereas the lower temperature, 350, is 70 plus. We can be more precise when we get into the question if necessary. And so when we're answering this question, it's a 5 marker, and so what that means is we will have lots and lots to say. We won't need to say everything that I write down in the bullet points, but we do need to come up with an approach. So this question very specifically is asking us to justify the conditions. And so when you are approaching this, we need to think, right, well, I need to mention the temperature because that is 450. We need to explain why it's 450. We need to mention the pressure at 200. And if we don't do both of those things, there's no way we can unlock the 5 marks. But probably looking at this, because we're only talking about yield from this graph, there's probably only 2 marks for each of those up for grabs, which means we've got a 5th or maybe even a 6th option for something else. And that something else for a question like this is about compromise. And in a reversible reaction question, a long mark, 5-6 mark question, if you don't use the word compromise, you've really missed a trick. So the first thing that we need to say is say what you see. So we've already explored this. Increasing the temperature will decrease the yield, or come at it the other way around. Low temperature increases the yield. And then we need to say, why is that the case? Well, that's the case because the forward reaction is exothermic. We can either memorize that about the Haber process, that the forward reaction is exothermic, or we can work it out using Le Chatelier. Or we've got a third option to do with temperature. We could say at low temperatures, the rate is too slow. We could throw in something extra from our knowledge beyond yield. And then when we move on to the pressure, we again say what you see. Increasing the pressure increases the yield. And then we can tie it into Le Chatelier, but this time we've got some help because we've got the equation to point us in the right direction. There are 4 molecules on the left-hand side and 2 on the right, because therefore there are less product molecules or fewer product molecules. Then we move on to our compromise. What we can say is the 450 degrees C, which is this line, by the way, that is in the middle. And that gives us a good rate. You can see that there's a bit of a cut-off in this period. Between 450 and 500, there is a huge drop-off in yield. And so 450 gives us a good yield, and it gives us a moderate rate of reaction. So this is a balance between rate and yield. Or you could come at this final question, kind of like turning it on its head and say, right, well, rate would be too low if we went to 350 degrees C. And so even though we get a high percentage yield, the rate is low, so it wouldn't be worth it. This final question is about a different type of reversible reaction where we are making hydrogen. And you can see we've got the equation here where we've got CH4, which you'll recognise as methane, reacting with water to make carbon monoxide and 3 molecules of hydrogen. And this will be relevant later. We have got, therefore, 2 molecules on the left-hand side and 4 molecules on the right-hand side. And so therefore the 2 on the left-hand side, that can be considered to be the lower pressure, and 4 is the higher pressure. And then we're also told that the forwards reaction is endothermic, which means the backwards reaction is exothermic. And our command is to state the conditions of temperature and pressure that would give the maximum yield of hydrogen. So we are wanting the equilibrium to shift to the right-hand side because that will give us the maximum yield of hydrogen, which is on the right. Now, when you approach a question like this, where you don't know what the conditions are, I suggest you think about it like this. So first of all, we know that we want it to go right because that's where we'll get the maximum yield. And so what's involved in a move to the right? Well, we want the equilibrium to move right, and by doing that, it will lower the temperature because, as we were told, the forwards reaction is endothermic, and endothermic reactions lower the temperature. So if we want the equilibrium to lower the temperature, before it does that, we need to first increase the temperature because the equilibrium is going to shift to oppose the change. And so we need to say we would use a high temperature, and that's because the forward reaction is endothermic, or the forward reaction takes in energy. If we apply the same approach with the pressure, we want the equilibrium to shift to the right, and we know already, we've said that there are 4 molecules on the right, which is a higher pressure, and so what we want is we want the equilibrium to therefore increase the pressure. And so first, what we have to do is the opposite. So we will decrease the pressure, and so the equilibrium shifts to oppose that and raise the pressure again. And so what we need to write for our answer is the pressure we would use would be a low pressure. And the follow-up mark for the second mark is we'd need to say, well, that's because a low pressure favours a reaction where more molecules are formed, or where 2 molecules turn into 4 molecules. And then the final question says, which of the following metals is most likely to be a catalyst for our process? Now, this actually comes from a different topic, the periodic table topic, where we know that catalysts are transition metals, or transition metals make good catalysts. And the transition metal from the selection that we've got is nickel. So our answer would be nickel. And the reason can just be quite simply, it is a transition metal, or it is a transition element. Okay, that's the end of this video walkthrough. I hope it was useful. Don't forget to check out all my other video walkthroughs that I've got, and I'll see you again soon. Bye-bye.